Hi everyone, today we are going to study spanning trees. A tree denoted by capital T is said to be a spanning tree of a connected graph denoted by G if this capital T is a subgraph of this capital G and then this capital T contains all vertices of this capital G. So in a simple language, if you have a connected graph denoted by G and this connected graph has a tree as its subgraph, then this tree, which is a subgraph of this connected graph, if it covers all the vertices of this connected graph, then such a tree, which is a subgraph of this connected graph G, would be called the spanning tree. So the three conditions for a spanning tree are that, first of all, there should be a connected graph. Then this connected graph must have a subgraph, which is a tree. And then this tree must cover all the vertices of the connected graph. Then you can say that such a subgraph, which is a tree, is a spanning tree because it covers all the vertices of the graph G. For example, the subgraph here, if you can see, there is a subgraph. I have denoted this subgraph in red lines. So this is an entire connected graph and these red lines are denoting the subgraph of this graph, right? So if you see the subgraph in red lines in the figure below, it is a spanning tree of the graph shown. So this is a graph and these red lines depict the spanning tree of this graph. First of all, the first condition should be satisfied for us to find a spanning tree, that the spanning tree is always found in a connected graph. So you can see this graph is connected because it is possible to start from any vertex and to reach any other vertex. So this graph is connected. Then the second condition is that the subgraph of this graph must be a tree. Now you can clearly see this particular portion is the subgraph of this graph. So this subgraph has no circuits in it. So I can say that this portion of red lines is such a subgraph that it has no circuits. Hence I can say that this subgraph is a tree, right? So the second condition is also satisfied. And the third condition says that this subgraph of the connected graph, which is a tree, must cover all the vertices of the graph. So in total, how many vertices are there in the graph? 1, 2, 3, 4, 5, 6 and 7. There are total 7 vertices. So this subgraph, which is a tree, must also contain all those 7 vertices. So if I consider this subgraph, which is the red lines, you can see that 1, 2, 3, 4, 5, 6 and 7. It is covering all 7 vertices of this graph G. So the third condition is also satisfied, that it is covering or it has all vertices of the graph denoted by G. So there is a connected graph called G. Then this connected graph G has a subgraph, which is a tree denoted by T. And this tree denoted by T covers all the vertices of the graph G. So I can clearly say that this T is what? This T can be called as the spanning tree. So this is how you find out a spanning tree in a connected graph. Since spanning trees are largest, why are they largest? Because they have the maximum number of edges. Out of all the subgraphs of a graph, the spanning trees are the one which are the largest because they have maximum number of edges. And why do they have maximum number of edges? Because they cover all the vertices of the graph. So they have the maximum number of edges. Hence the spanning trees are the largest trees among all trees in the graph G. The graph G may have several such trees as its subgraph, but it is only the spanning tree which is the largest, because rest of the trees may not have all the vertices of the graph, hence they do not have maximum number of edges, but it is the spanning tree which will cover all the vertices of the graph G, and hence it will have maximum number of edges. So for that reason, because the spanning tree has the maximum number of edges, it is also quite appropriate to call a spanning tree a maximal tree subgraph or a maximal tree of G. So that is why a spanning tree is also sometimes called a maximal tree subgraph or a maximal tree of the graph G. A spanning tree is defined only for a connected graph. This is the thing that I told you initially also, that the first condition to find a spanning tree in a graph is that graph must be a connected graph, because a tree is always connected. We have already studied tree, and we know that for a tree, the two main conditions are that it must be connected. If a tree is not connected, it is not considered a tree. So it must be connected and it must be circuitless. Only then you can call it a tree. So that means if you have to find a spanning tree, it is quite obvious that you can find it only in a connected graph and not in a disconnected graph. Now each component, if I talk about a disconnected graph, then each component of a disconnected graph by definition is connected. It is a possibility wherein you have a disconnected graph, and then you know a disconnected graph has several components. It can be made up of 2 components, 3 components, 4 components, and those components in themselves are connected, right? So each component of a disconnected graph, however, can have a spanning tree. So it is not possible for a disconnected graph to have a spanning tree, but all those components of the disconnected graphs which are connected can have a spanning tree. Okay, so a disconnected graph with k components has spanning forest consisting of k spanning trees. To understand this, first of all, you must know that a collection of spanning trees is called a spanning forest. And if there is a disconnected graph, and if it has k components, and if I assume that every component has at least one spanning tree, right? One component may have more than one spanning tree. But if I assume in a hypothetical situation that every component of the disconnected graph has only one spanning tree, so that means if there are k components, I can find k spanning trees in those k components, and hence that means I have a spanning forest. A collection of trees, as I told you, is called a spanning forest or a forest. And so in a disconnected graph with k components, you can find k spanning trees forming a spanning forest. Finding a spanning tree of a graph G is simple. Now if I tell you, I have just told you how you can find a spanning tree in a graph, but I will just revise it, that how do you find a spanning tree in a graph G? It is very simple. First of all, if G has no circuits, it is its own spanning tree. If the graph G does not have any circuits, it itself is its own spanning tree. But if G has a circuit, then delete an edge from the circuit. Delete one edge from the circuit if the graph G has a circuit. So this will still leave the graph connected. Do not worry about the graph being disconnected, because just removing one edge from the graph will remove the circuit, but it will not make it disconnected. So if a graph G has a circuit, first of all you delete just one edge from that circuit. This will still leave the graph connected. You still have a connected graph after removing one edge from the graph. Now if there are no more circuits, then you've already found a spanning tree by removing one edge from the graph. But if there are more circuits, then you have to repeat this operation. That means after removing one edge, you found that there are still circuits in the graph, then you remove one more edge. Then after removing that second edge, if you still see circuits in the graph, remove one more edge, right? till the graph is connected. So removing one more edge or two more edges from the last circuit leaves the circuit free graph. Now the graph becomes circuit free. So you have to basically keep removing the edges from the last circuit, right? Till you have a last circuit in the graph, you have to keep removing these edges, and this will leave a circuit free graph that contains all the vertices of the graph G. So basically edges are being removed to remove the circuit, but still you have the vertices, of course. So it will give you a circuit free connected graph that will contain all the vertices of the G, and hence you found your spanning tree. If you consider this particular example, this is what has been done over here. This was a connected graph having circuits, right? There were circuits in this graph. Like you have parallel edges. There's a closed circuitry in this graph. So basically the graph has circuits. Now what was done? First of all, this edge is removed, the graph still has circuits. Then this edge is removed, the graph has still circuits. This is removed, still it has circuits. This is removed, still it has circuits. This is removed, still it has circuit. This is removed, still it has circuit. This is removed, still it has circuit. This last circuit is now left. It is also removed. Still the graph is connected, and now since all the edges forming circuits have been removed, what we are left is with a tree which contains all the vertices of the graph, and this particular tree is then your spanning tree. So this is how you can find a spanning tree in a graph. Every connected graph has at least one spanning tree. A connected graph may have more than one spanning tree, but every connected graph will have minimum one spanning tree. A spanning tree is also sometimes referred to as the skeleton or scaffolding of the graph G.